Yes.
So basically what I got here is the proof of Gaussian integral by Wallace product, or maybe just by using the squeeze theorem actually would be easier. So what I'm trying to do here is basically, well, so what squeeze theorem is just making, if that's the case and essentially x equals to 3, that's what squeeze theorem is basically. So so what I want to do first is that I want to make some integral 0 to infinity e to negative x squared dx. So that's the Gaussian integral. And I want to find some function that's like strictly less than or strictly larger than the Gaussian integral and make these two equal to each other somehow. And then say that the Gaussian integral equals to some specific value, right? So what I thought of is these two functions, like you can see. So x would be the variable and n would be just a arbitrary number that just sticking around. So I've made an easy graph that's just on the right side. So
Yes.
yeah, that like you can see that this inequality makes sense. And now what I want to do is to integrate all these functions because just these functions doesn't really make sense. So for Gaussian integral, I'm just going to make it 0 to infinity dx and integrate like that. And for the right side of the inequality, I'm going to make it 0 to infinity. And then on the left side, I'm going to make it 0 to 1 range. And that makes sense because 0 to 1 range is like, it's just that part of the function, and the other one is like that part and that part, which still makes sense as an inequality. Okay, now just just for now, forget about this inequality, and I'm going to define in as integral of 0 to pi on 2 sine n x dx. Just forget about this part for a moment. Right, what I'm trying to do with this function is just trying to find a recurrence formula for this. And how I'm going to do that is just 0 to pi on 2 sine n minus 1 x and sine x dx. So what I'm trying to do here is integration by parts. And I could do all the steps, but that's going to take a bit of time. So I'm going to skip a bit of steps and
Just
you
the final.
will,
Yeah.
yeah. Yeah, so you will get sine n minus 2x 1 minus sine squared x dx. That's the what you'll get from this integration by parts. So and you could expand it as 1 plus 1 integral 0 to pi on 2 sine n minus 2x minus integral 0 pi on 2 sine n x dx. dx. So what you can see here is actually what we've started from here, which we've defined as in. So what this means is that I can actually make a recurrence formula from this by just rearranging a bit and phrasing this part as in. And this part is actually, you can phrase it as in minus 2 because it's power of n minus 2. And if I just play around and rearrange it, I would actually get in equals to n minus 1 to the n in minus 2. All right, just remember this recurrence formula. It's very important. And this actually works for cosine as well. If you just do it, then that would actually make sense. All right, let's just go back in the original inequality that we've made earlier and let's just start integrating the first function. Okay, how am I going to do this? I am going to use the substitution method by substituting sine theta, actually, sine theta into x. And then dx d theta equals to cosine theta, and as x theta as 0 to 1, 0 to pi. All right. So if I just substitute it in, this would become 0 to pi on 2, 1 minus sine squared theta to the n cosine theta d theta. And you can see that this part is actually cosine squared theta. We can just change it into So therefore, this would become cosine to the power 2n theta plus 1 d theta. And this is actually the definition that we've made here. 0 to pi on 2 cosine n. Actually, just substituting in 2n plus 1. So we can rephrase this function as I 2n plus 1. Okay, now I've actually already written the answer for the integral for the other parts here, because time-wise. So for the right-hand side of the inequality becomes that, and yeah, substituting y for the Gaussian integral part as well, and it just becomes that. So this would be the final inequality for the inequality. So okay, let's just focus. Before that, I actually don't like how it looks like. So I'm just gonna multiply everything by root n. So that's gonna disappear, root n, and then root n. It's gonna look like that. And then now I'm gonna play around with this part of the inequality for now. So basically, what I'm trying to do here is, okay. So I'm just going to times it by 2n minus 1, 2n, times it by 2n, and then 2n minus 1. That's completely valid because that's just times it by 1. And so recall the the recurrence formula that we've made. Where do you go? Yeah, n minus 1 over n, I n minus 2. So that is actually, yeah, that is actually this part. What? N minus n, yeah, this part here. If we're substituting I n minus and I 2n minus 2 in here, that becomes yeah, not the root n part. Wait, yeah, this part here. That actually becomes, wait, no. 2n minus 1, 2n, I 2n minus 2. So I can just substitute in I 2n here actually to make it look more pretty. I 2n, 1, 2n minus 1. Okay, so what I could do here.
Sorry,
now,
Sora, for interrupting you, Sora.
Yeah. Yeah.
Do you have the slides that you prepared for presentation? So no need to write here. I appreciate your work. You have good method, but this will take a long time. Just show us how Gaussian integral can be proved by Wall's product.
Okay.
That's it. So no need to do the details, the calculation, everything by using pen and everything like in tutorial class or whatever. Okay.
Okay.
So to the main point straight away.
Okay. So basically afterwards, I've just so that part. So I'm just substituting this thing into the original inequality and then times it by I2n plus 1 over I2n plus 1, which is 1. So that's completely valid. And then, okay, forget about that inequality again. And what I'm showing here is that if the domain is to 0 to pi and 2, then the range would be to 0 to 1. So basically means that multiplying sine x with, powering by a larger number in sine x would get a smaller result because that's in the range of 0 to 1. So integrating with that would be obviously would have the same inequality. So I2n plus 1 is strictly greater. That inequality would make sense. So now I2n, okay. So what I'm trying to do here is just divide I2n, I2n with each other, and that formula would appear here. And what we want to try and do here is just rearrange this part. So substituting this formula into this recurrence formula that we've made initially, and that actually would become like or something else. So anyway, if we substitute in, we get this formula that is like limit. So this inequality, and then this right-hand side by L'Hopital's rule, we can say that it equals to 2 on 2, which equals to 1, which therefore means that the middle limit I2n plus 1, I2n is equal to 1. So after we got that formula, we can go back to the original function that we had here. And you can see that we have this part identical, completely identical in the range. And this part is actually, we can just make it disappear by L'Hopital's rule. So take the limit on all the side. And we can say that by L'Hopital's rule and by Square's theorem, the Gaussian integral equals to the limit of n approaches infinity root n I2n plus 1. Okay, so what root I2n plus 1 actually is here's the trick actually. You can split I2n plus 1 just like that. That's completely valid. And then I2n, which is just 1, so you can just make it like that. And then just forget about that for a sec. And then this is the answer. This is what we get when we expand the recurrence formula for I2n and I2n plus 1. And then if we multiply I2n times I2n, then we get that. And if you look carefully, then we can like cancel everything out. Just like that. And then what we get left is 2n plus 1 and then pi on 2. So yeah, and if we look here, that's the multiplication part, and then that's like the what we proved initially, just like that it equals to 1. So therefore, if we substitute in, it becomes like root n, and then if we take the limit of that, it's just there. That becomes 1. That this part becomes this by L'Hopital's rule, it becomes just n disappears and 4n, and that's the root. So yes. Meaning root pi on 2, which is the original Gaussian integral. Therefore, the purity.
Okay. Thank you very much. Good. Yeah, I like your method of proving, which is as always a real analysis method. Okay, by using a proof. Yeah. Maybe to make your job easier. Okay, to ease your job, that is, it is better to prepare the slides and just comment them rather than writing here, but it is hard thing for you and made you going behind the time. However, you did a great job. Thank you very much. I have just one question because the time is, what is the Wallace product?
Well, Wallace product is just saying that it's a pretty cool formula actually. It's like the sum of like 2n on 2n minus 1.
Why we call Wallace product? Why? What's the
why? Yeah, I think someone called Wallace made it or something. I don't know.
If you go to the first slide, First, go up to the beginning.
Yeah.
It's okay. You said here, okay, you put the integral. I think this is pi, integral from 0 to infinity e power negative pi or nx squared. The last step to the left of the graph.
Mm-hmm.
Yeah. So you put this function between two boundaries. Yeah.
Yeah.
When you put boundaries around it, that's Wallace product. You got. Because you put wall, okay? That's what we call the Wallace product, the name.
Oh, okay.
Yeah. Okay.
Right, can I just quickly say,
Yeah.
Sora, thank you for that. Now listen, there are elements. You're obviously we're talking about the time and the presentation. Now that issue of time and presentation, that's a teaching problem. Okay, so
Yeah.
when you're developing your run sheet for your presentation, the timing and the way you're going to interact with what your thoughts are, that's the teaching problem. So don't worry too much about that. I mean, this whole process is designed to help you improve all aspects of what you're doing. But I want to say to you, the actual content and the way that you present is actually quite good. If you could just hone a little bit on the timing and the use of slides as Talib suggested, and speak only to the gaps that you really planned for, you could easily make this fit into a suitable time frame. And the enunciation of the ideas is actually very clear. So it was actually a very good example of maths teaching. I want to say that to you outright. Okay, so you can go away with your head held up high, but remember, I guess, all the feedback. All right, I'll stop there and tell him it's over to you. I think you're pretty much done.
Okay, yeah, thank you very much, Jason, for the comments. Okay, Sora, just go down a little bit.